Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss the speed of a second order unimolecular reaction. Okay, that means the kinetics of a second order unimolecular reaction. As you know, our ultimate agenda is to find out the speed of the reaction. And what is the second order unimolecular reaction? Let me give in brief. And unimolecular reaction talks about 2A gives rise to B, and if you see minus Ra is equal to minus dCA by dt is equal to kCa square. That means the order 2 comes from only the molecule A. Imagine that these two molecules have to collide, for the reaction to happen. So that is why two molecules which has to come together to form B. And the thing is, what is bimolecular second order? Simple. Instead of 2A gives rise to B, if A plus B gives rise to C, that is one molecule of A and one molecule of B has to come closer to react to form product, then this comes under bimolecular second order reaction. Here it is only two molecules of same molecule A, that is why it is called kinetics of second order unimolecular reaction. And let us further do the process, and minus Ra is equal to minus dCA by dt is equal to kCa square. So let us integrate, because we are using integral method of analysis, and bring all the concentration terms on the one side, time and time on the other side. You get minus dCA by Ca square is equal to k into dt. Now we have to apply the limits to solve the integral. At t equal to 0, that means I am conducting the reaction in a batch reactor, as you know, the entire, that is why it is called dCA by dt. At time t equal to 0, the concentration of A in the reactor is equal to initial concentration, which is Ca0. At time t equal to t, any time after the reaction happens, and Ca is nothing but concentration of A at that time. So Ca0 to Ca, time t equal to 0 to t, if I integrate, okay, 1 by x square into ds, the integral of 1 by x square into dx is equal to minus 1 by x. 1 by x integration minus 1 by x, you can think 1 by x minus 1 by x square, minus 1 by x square, the integration is 1 by x minus 1 by x. So 1 by Ca, for the limit Ca0 to Ca is equal to k into 0 to t, dt is nothing but t. Okay. Then let us apply the limits. First limit is 1 by Ca, second limit is Ca0, 1 by Ca minus 1 by Ca0 is equal to k times t. Now you can see the equation, the one on the other side is y, the one on the right side time is x. Two variables, that is one variable is y, another variable is x, and the k is named as slope of the equation, y equal to m times x. That means whatever assumption, example, there are some experiments I have conducted in this batch reactor. I have to prove whatever the experiments I have conducted, that is the unimolecular second order reaction is valid. If the experiments and the model both saying the same thing, that means whatever the model I have assumed is correct. To do that, I have to plot y and x, that is 1 by Ca minus 1 by Ca0 on the y axis, the time is on x axis. Then I have to plot my experimental data on that particular graph, and if the line is passing through all the experimental points, that means whatever the experiments I have conducted in the batch reactor is of unimolecular second order reaction, otherwise whatever the model I have assumed is wrong. So, and let us plot this equation on the graph. Before that, if I separate out Ca on one side and the other constants and variables on the other side, Ca, that means exit concentration, that means the concentration after the reaction is nothing but 1 by initial concentration plus k times t. K is my second order rate constant and t is the time. Okay, let us keep this in mind for the later picture of the story. Let us see whether we have second order or not. So, I have conducted some experiments. Okay, I initially have kept 50 moles per liter of reactant in this reactor. I have started conducting the reaction. Every 5 minutes, I have extracted some sample out of the reactor. I have measured the concentration of A. The initial concentration of A is 50 at time t equal to 0. As the time proceeds, the concentration of A is reducing because of the reaction, the concentration of A will reduce. And I know 1 by Ca minus 1 by Ca0. Okay, this is what I have to plot. For initial condition at time t equal to 0, Ca is nothing but Ca0, which is 50. 1 by 50 minus 1 by 50, not by 0. In the second, after 5 minutes, my Ca is 1.92. That means 1 by Ca minus 1 by Ca0. Ca0 is nothing but 50 mole per liter. Like that, I have calculated for all the times what is my concentration of A and what is the factor 1 by Ca minus 1 by Ca. Now, I have the data of time 1 by Ca minus 1 by Ca0. Now, I have to plot 1 by Ca minus 1 by Ca0 on the y axis and the time t on x axis, and this is what the time, and you can see this is time and this is 1 by Ca minus 1 by Ca0. And in the Excel or any other line fitting software, if a line is passing through all the points are nothing but this experimental points. The line is called fitting line for all the points. If the line and the points are matching better, that means R square value is more than example 0.99. That means whatever the model I have assumed, second order unimolecular reaction and experiments, both are following the same trend. That means the reaction which is happening in this batch reactor is nothing but second order unimolecular reaction, and the slope of this equation is nothing but K. K is your rate constant of this second order unimolecular reaction. This is 0.1, 1 by minute and liter per mole. How I got this unit? Here it is. I know dCA minus dCA by dt is equal to kCA square. From that, what is K is nothing but minus dCA by dt divided by Ca square. What is the unit of concentration? Mole per liter. What is the unit of time? Minute. What is the unit of concentration square? Mole per liter whole square. Few things cancels out, and finally the unit of the rate constant is nothing but 1 by minute into liter per mole. This is the rate constant, unit of this rate constant. Okay. The main important thing is, just a second, the concentration and time. When you plot the concentration, if you increase the time and observe the concentration is getting decreased. Okay, this is the line, line equation. Initially the concentration will be high because at the start of the reaction the initial 50 mole per liter. As the time proceeds the reaction, A will get consumed, the concentration of A will reduce. And you can see it is not a linear line, it is a non-linear line. If you remember my lecture on kinetics of zero order reaction, the line is a straight line because the speed of reaction everywhere is the same because the slope is same everywhere. And when you talk about the first order reaction, it is a logarithmic line. That means the speed of a reaction at the initial time will be higher and the speed of the reaction at the later time will be lower. Similarly, if you draw the same analogy, and for the second order reactions, even the curve will be more steeper. That is why, and you can see the steepness is very high. Okay. Even at the initial stage, the speed of reaction even more for the same rate constant value I am talking about, do not worry. That means more is the order, that means starting speed will be higher because the slope will be much steeper. Okay, that is what the takeaway. Let us now calculate the speed. I am talking about the rate of reaction or speed of reaction. Let us see the speed of reaction in a second order unimolecular case. And this is the time and concentration data. It is the same. And let us measure the speeds. I know the rate minus Ra minus dCA by dt is equal to K into Ca square. That means the speed is nothing but K times Ca square. I know K is 0.1 and Ca square is nothing but the concentration at that time. At the time t equal to 0, the concentration is maximum. So, the speed is 0.1 into 50 square, that is 250 mole per liter per minute. That means every minute 250 mole per liter will be reduced. That means the concentration will be reduced to 250 mole per liter every minute. But here we do not have the 250 liter inside the reactor. Here we have the initial concentration is 50 mole per liter. So, this 250 mole per liter per minute the speed is, the reaction will start at that kick. Okay, it does not mean that in 1 minute the concentration will be reduced to 0, it is not like that. At this 50, the reaction will kick start, okay, at the speed of 250 mole per liter every minute. Okay, but as the concentration of A is getting reduced in the reactor, that means the second instance the concentration is 1.92 after 5 minutes. At this concentration the speed is 0.1 into 1.92 square, which is 0.36 mole per liter per minute. As you can see, if the concentration is more, the reaction will try to proceed at the high speeds. As the concentration of A is reducing, the speed is also reducing. Okay, you can see the starting speed is, because at 50 mole per liter concentration, that starting speed is 250 mole per liter every minute. As the concentration is dropping, along with the concentration the speed will also drop, because the speed is proportional to concentration square. That is, more is the concentration, speed is the more, less is the concentration, the speed is the less. That is what the takeaway. That means the slope of the line will be higher as the order is rising. Okay, and here the equations are in terms of concentrations. Here the same equation I have represented in terms of conversions. I know 1 by Ca minus 1 by Ca0 is equal to Kt, the same equation we have taken, and you take the division multiplication, Ca0 minus Ca by Ca times Ca0 is equal to K times T. I know Ca0 minus Ca from the conversion, Ca0 minus Ca by Ca0 is into x, okay, is equal to x. So, like that Ca0 minus Ca is nothing but x times Ca0. What is Ca? Nothing but 1 minus x into Ca0 into this Ca0, that is equal to K times T. Now, 1 Ca0, 1 Ca0 cancels out and Ca0 went this way, and final equation is x by 1 minus x is equal to K Ca0 into T. And now you can see this equation, the same equation is in terms of conversion, this is in terms of concentration. Now you have to plot y equal to mx. The y is x by 1 minus x is on y axis, the x is the time is on x axis. Now if you plot the graph, the slope, this is how we can check, and if the experimental points are matching with that of a line, that means whatever the assumption we have taken based on the model is correct. So, if data points are matching with that of a line, and the slope from this graph is nothing but K times Ca0. If slope is equal to K times Ca0, then K is nothing but slope by Ca0. So, in this way also you can able to get the rate constant of a reaction. Hope you understand what is the how we are proceeding. We have 0 order speeds, we know the first order speeds, we know the second order speeds. 0 order speeds means there is no change, which whatever may be the concentration, there won't be any change in the speed. First order means first order dependency, more is the concentration and more is the speed, that is Kca. Less is the concentration, less is the speed, that is Kca. Okay, and even it's for second order, even the speed is much more higher when the concentration is more. When this at high is the concentration, speed is Kca square. Okay, like that, lower is the concentration, low is the speed according to the Kca square. Okay, I hope you have understood the basic difference between 0 order speed, first order speed, second order speed. So let us meet with a new lecture. Thank you.